So what we're going to be doing today, we're going to continue on talking about Thevenin and Norton equivalent circuits, which was saying if I have very complicated circuit and I'm interested in like voltage, current, or something in the circuit, I can basically simplify down that very complicated circuit to a very simple circuit that we're familiar with, and then go from there. So let me quickly review what we had. So let's just say I have a black box. And this black box could be very complicated, right? It could have a bunch of like dependent sources, independent sources, a bunch of resistors. Could be like anything. So this contains many independent or dependent or both sources with a bunch of resistors, right? And this is connected to some terminals A and B, and that is connected to some load value, let's just say a resistance, that we're interested in something about that resistance. For example, voltage across it, current through it, power dissipated by that resistor, something about it, right? We said it is possible to just replace that black box by either a voltage source with value Vs, followed by a single resistance Rs, which is a representative of our black box, and therefore this is A, this is B, or a current source followed by a single resistance in parallel with it as another representative of the black box. And if this is a representative of our black box, I can stick the resistance back in here or back in here. And since these circuits are very simple circuits, I could solve for whatever I am interested in. Voltage across the resistance, current through it, and everything, right? The idea was, since these circuits are supposed to be a representative of our black box, therefore I have to determine Vs, Rs, and Is such that the external behavior of these two circuits, these two equivalent circuits, are exactly the same as the external behavior of the black box, right? That was our deal. We said, if I remove this load and look at the open circuit voltage across A and B, since there is going to be no current through Rs, voltage across these terminals, which is B open circuit, is exactly this Vs. So we said Vs must be B open circuit, which implied, since this little circuit down here is equivalent to the black box, so if I do the same thing and look at the terminal AB in the original circuit, leave it open, and find voltage across those two terminals, that should be Vs. We said the same thing about Is. We said if we remove this RL and short out A and B, since current always takes the path with the least resistance, Is must be I short circuit. And again, since this circuit here is a representative of this black box, so if I do the same thing over here and short out between A and B and find current through it, that should be Is, right? We talked about this before. We also said, since this circuit is equivalent to this black box, this circuit is also equivalent to this black box. If I look at the external behavior of this circuit, basically from A to B, that should be the exact same as the external behavior of this circuit from A to B, right? These two circuits, therefore, are equivalent as well, right? If I look at voltage across AB over here, which is open, what is voltage across AB? That's this Vs, right? Therefore, voltage across AB over here, if I leave it open, must also be Vs. If voltage across AB is Vs, voltage across this Rs is also Vs, right? But I already know Rs times Is is Vs. So I can find Rs just by looking at Vs and dividing it by Is. Or we know Vs is V open circuit. I know Is as I short circuit. So if I compute V open circuit and divide it by I short circuit, that would give me that Rs. But we said this is a very general case, right? Today, what we're going to be doing, we're going to actually have like a subcategory of circuits that we can have like a shortcut to find this Rs. So we don't really have to like compute V open circuit and I short circuit and divide them, right? So this one down here, this Rs, is due to equivalence of simplified circuit. We call this representation of this black box Thevenin equivalent circuit. And this representation, Norton equivalent circuit. Right? And we showed these two circuits exist. Right? What we're going to be doing today, we're going to have like a recipe that we can follow through and find this simplified circuit over here. So we're going to start by having a recipe for Thevenin equivalent. And then we're going to do a few examples on that. And then we're going to move on to like a recipe that we can always follow through and find the normal. Okay. So let's start by Thevenin equivalent circuit. How to apply Thevenin theorem. Remember, the whole idea here is that I have like this black box. Between terminal A and B, there is an element. And I want to replace this black box by a circuit that looks like this. Right? The first step is to determine the load. What's a load? A load is an element in the circuit that we're interested in something about it. In this case, it was basically this resistor. It could be any element in the circuit. So the load is an element in the circuit that we are interested in something about it. Current, voltage, power, anything. Right? As soon as I determine what the load is, the rest of the circuit is my black box. Right? Now I know what the load is. To be able to form this circuit, I need to know this Vs, and I need to know this Rs. So the second step is to find Vs, which we call it like Vthevenin. Okay. To do this, we remove the load and leave the terminals open. Then we find voltage across those terminals. Right? Basically, Thevenin is our V open circuit, as we discussed before. Right? The third step is to find Rs, which we call it R Thevenin. Obviously, we have like that general Vs divided by Is thing, which is V open circuit divided by I short circuit. But let me just divide it into like a subcategory that can make our lives like a lot easier if the circuit we're dealing with falls into that category. And then, of course, I'm going to talk about like a general case when we need to like find V open circuit and divide it by I short circuit. So case one, let's just say there is no dependent source in our black box. There is no dependent source in the black box. If that is the case, to find our Thevenin, we're going to zero out all the sources that we have, and we're going to left with a resistive circuit, and then we can find our equivalent. Right? So the idea here is that zero out all the sources and compute the equivalent resistor. How do we zero out sources? We set the value equal to 0, right? But what does that mean for a voltage source? It means we're shorting it out. We're replacing it by a wire. What happens to a current source? We're just going to leave it open, right? So it's an open circuit. So let me just quickly add that in. Zeroing it out means if I have a voltage source, I have a short circuit. If I have a current source, I have an open circuit. Right? So this portion is like very easy. Right? I'm going to take a look at my black box. If there is no dependent source, I'll find the equivalent resistance by zeroing all the sources. Case 2 is the general case. When I look at the black box, not only is there some independent sources, but there might be like, dependent sources. So there is dependent sources in the black box. If there is a dependent source in our black box, since the value of the dependent source is being controlled by something else in the circuit, I cannot zero it out. Right? So I have to go back to the general way of computing RS. So in this case, we find I short circuit, again, by removing the load and shorting it out. Then our Thevenin is V open circuit divided by I short circuit, which is the very general case that we had, right? Last step, I have both Vs and Rs. I can form the Thevenin equivalent circuit for the equivalent circuit and stick the load back in and solve. Right? Let's do an example to see how we can apply all these steps. Right? We're going to start by a simple example, and then we're going to work our way up to like harder examples. Okay? Example 1. Let's just say I'm given this circuit. 12 volts, 6K, another 6K, a 2K, and a 1K. And the question is asking me what is V out. Right? I mean, if you look at this circuit, this is like very simple circuit, right? We don't really need to do like Thevenin equivalent. But for the sake of, going through all the steps and see like how it works, let's just start by this simple circuit. The first step is to determine the load. What is the load here? What is it? The load is the element in the circuit that we're interested in something about it. In this circuit, I'm interested in voltage across this 1K. Therefore, this 1K is my load. So this is my load. Call it RL. The rest of the circuit, whatever I have over here, is my black box. And the idea is that I want to replace this black box by the Thevenin equivalent. So the first step is to determine the load. Second step is to find Thevenin. How do we find Thevenin? We're going to remove the load. We're going to leave those terminals open and find voltage across those terminals. So my circuit would look like this. I have this 12 volts. I have the 6K, 6K, 2K. I leave these two terminals open, and I need to find this V open circuit here. Right? What I'm claiming here is that V open circuit here is exactly the same as voltage across this 6K. Why? Why is that? Because there's no current going through this 2K. This is open circuit. Right? So there is no voltage drop across this 2K. So whatever voltage I have across these two terminals must jump across this 6K. Right? If you cannot see it that way, you can always write a KVL here. Right? Since current through this 2K resistance is 0, voltage across it is 0. Therefore, 0 plus V open circuit equals voltage across the 6K. Right? But what is voltage across 6K? That's a voltage divider, right? So I have 6K divided by 6K plus 6K times 12, which is 6. Right? That is the open circuit, which we know that is exactly the same as V7. Third step is to find R Thevenin. To find R Thevenin, we're going to look at the black box. We know this portion of the circuit is our black box. Is there any dependent source in it? No. So we fall into the first category. So to find our Thevenin, I have to zero out all the sources I have and find the equivalent. How do I zero out this voltage source? I basically like replace it by a wire. So my circuit would look like this. I have this 2K, and I have to find R equivalent. What is R equivalent here? Well, it's like super easy, right? We've done this like many, many times. This 6 and this 6, what is the relationship between them? What is it? They're in parallel because they're sharing the exact same head and exact same tail. So it's 6K in parallel with 6K, which is a 3K. And what I'm claiming is that this 3K is in series with this 2K. It is, right? So my R equivalent is 3K plus 2K, which is 5K. Right? Last step is to form the Thevenin equivalent. I know V Thevenin, I just computed it, it's 6 volts. I know R Thevenin, which is R equivalent here, which is 5K. Right? Now I have to stick the load back in here. So this is my load. This is RL. The question is asking me, what is V out? What is V out? That's a voltage divider, right? So V out, this is 1K. V out is 1K divided by 1K plus 5K times 6, which is 1. Right? Any question on this? Are the steps clear? Yes? No? Does that make sense how we computed R Thevenin? Yes? So let's move on and do one more example, which is a little more difficult than this. Example. Let's just say I'm given this circuit. So 2 milliamps, 4K, at 2K. I have another 2K followed by a 4K. And I have a bunch of sources. This is 12 volts, this is 8 volts, and this is 6 volts. And the question is asking me, what is this I out? Right? What is the first step? Is to determine the load. What is load here? What is it? That's that 2K resistance over here. Why? Because I want to find current through it. That's the element in the circuit, and I'm interested in something about it. So this is my load. If that is the load, the rest of the circuit must be the black box. Right? So the second step is to find V Thevenin. How do we find V Thevenin? We're going to remove the load, leave it open, and find voltage across it. And we call it the open circuit. So if I redraw the circuit would look like this. It's a 4K. I leave this open. We call that the open circuit. That's a 2K. That's a 4K. And I have the rest of it. Right? You with me? What I'm claiming is that finding this to be open circuit is extremely easy. I just need to write one KVL. You with me? I just need to write a KVL right here. Can I? To be able to write a KVL, I need to know voltage across this. What I'm claiming is that I know exactly what voltage across this is. How? To find voltage across this, I need to know the value of the resistance, which I know it's 4K. And I also need to know current through it. I know exactly what current through it is. What is it? That's just 2 milliamps. Because this is open circuit, so there is no current leakage here. So all 2 milliamps is just going to flow through this 4K. So if I write a KVL in this loop, I have 4K times 2 milliamps plus 6 minus 8 minus V open circuit, that equals to 0. This is 8 volts. 8 and 8 cancel. It tells me V open circuit must be 6 volts. Right? What is the next step? I have to find R Thevenin. To find R Thevenin, I'm going to look at my black box to see if there is a dependent source in it or not. Is there? No. So I fall into the first category. So I have to zero out all the sources that I have and find the equivalent. What do I do with these voltage sources? I short them out. Just put a wire there. How about this 2 milliamps current source? I just open it. So if I redraw the circuit, find R Thevenin, my circuit would look like this. Just put this over here so you can see. So I open this. This is my terminal A and B. This is the 2K. I short out these. And then I have this 4K up here. And I have to find R equivalent. What is R equivalent? What is R equivalent here? What is the relationship between this 2K and this wire over here? They're in parallel. How about this 4K and this wire down here? What happens if I have a resistor in parallel with a wire? What is the equivalent? It's 0. So it means that it doesn't really matter. So this portion does not really matter because it's 2 in parallel with 0, which is a 0. This portion does not really matter because it's a 4K in parallel with a 0, which is 0. What is my equivalent? That's that 4K on the top. Right? Next step is to just form the equivalent circuit. For Thevenin circuit, I have V Thevenin, which I know it's exactly the open circuit, which is 6 volts. I have R equal, which is R Thevenin, which is 4K. Right? Now I have to stick the load back in here. What is my load? My load is this 2K. So put it back here. Right? The question is asking me, what is this I naught? Right? I naught is very simple. It's just Ohm's law. Right? I naught is Ohm's law, which tells me that 6 divided by 4K plus 2K, which is 1 milliamps. Right? Is that clear? Does that make sense what's going on and how we're approaching a Thevenin circuit? Let's do one more example. Let's just say I'm given this circuit. I have this 1K followed by a 2K, another 2K here, a voltage source with value 12 volts, a current source with value 2 milliamps, and a 1K resistor here. The question is asking me, what is V out? Right? The first step is to determine what the load is. Which one is the load? This 2K, because I'm interested in voltage across it. So this is my load. What it means is that the rest of the circuit is my black box. Therefore, the second step is to find Thevenin. How do we find Thevenin? We're going to remove the load, leave those terminals across the load open, and find voltage across it. Right? So I have this 1K. I have this 2K. I have this V open circuit. This 12 volts. And this 2 milliamps, followed by this 1K. What is V open circuit? What is it? Just need to write a KVL in this loop. But to be able to write a KVL in this loop, I need to have voltage across that 2K. Do I have it? I do. I know the value of the resistance, and I know the current through it. What is current through it? Yeah. So if I write a KVL here, let's just say I'm going this direction. What do I have? I have negative 12 minus 2K times 2 milliamps plus V open circuit. That should be 0. Did I write it correct? Is this correct? Is this negative 2K times 2 milliamps or positive? Exactly, it is negative. So I wrote it correctly. And the reason for it is that the direction of the current is this way. It's going from right to left. But the loop direction I considered is a clockwise, it's the opposite direction. Right? So I have to like make up for it with a negative sign. From here, I can compute V open circuit, which is 16 volts, which I know that's V Thevenin. Right? Third step is to determine R Thevenin. To find R Thevenin, I'm going to look at the black box, right? And I'm going to see if there is a dependent source in there or not. Is there? No. So I can use the shortcut. I can zero out all the sources I have and find the equivalent resistance. So third step is to find R Thevenin. If I do that, I have to zero out this source, which means I have to replace it by a wire. I have to zero out this source, which means I have to open it. So my circuit would look like this. I have this 1K, 2K. This is open. This is like this. And I have this 1K. And that's it. I have to find the equivalent What is our equivalent here? What is it? That's a 2K, right? Because if I look at these two, obviously they're in series, right? So I can replace it by one resistance, which is 2K. But what I'm claiming is that it doesn't even matter. Why? Because it is in parallel with this wire down here. Since it is in parallel with a wire. Do you see it? It is actually in parallel with the wire. This is the head of the equivalent. This is the tail of the equivalent. And this is the wire. Right? So this 2K over here is in parallel with the wire. So it goes away. So the only thing I have is this 2K. So that is my R equivalent, which is R Thevenin, right? Last step is to draw the equivalent, which I know I have V Thevenin, which is 16. I have R equivalent, which is R Thevenin, which is 2K. I'm going to stick the load back in here. I have this 2K load here. And the question is asking me what is V across that 2K. So this is V out. What is V out? Well, it's a voltage divider. It's 2K divided by 2K plus 2K times 16, which is 8 volts. Right? Any question on this? Is that clear? So for now, I'm not going to do an example on the black box with a dependent source. I'm going to just postpone it to after we talk about Norton equivalent. So we know how to compute I short circuit. And then we know how to compute those two things. We can basically divide them up and get the R Thevenin. So I'm just going to postpone it to that time. But does this make sense? Right? So what we learned so far is that if I have a black box, right, I can replace that black box by a voltage source followed by a single resistance, right? So if I have a black box, I can always replace it by a circuit that looks like this. And if I have some load, I can stick it in here. And I have this circuit, right? What if I told you you don't know this value of the load, but you're going to have to determine this value of the load such that this load has the maximum power? You can do this, right? Given the fact that you know V and R, you should be able to determine this R load such that it has the maximum power. So let me just write down the question. Given V and R, determine RL such that it has maximum power. How do we do this? Well, I know exactly power dissipated by that RL is, right? It's voltage across it times I, or since it's a resistance, I know that the power is R times current through it squared, right? So let's call current through it I. We know power dissipated by this load is RL times I through RL squared, right? But I through RL is exactly the same as I. And based on Ohm's law, it is V divided by R plus RL. Right? I can combine these two things. I know voltage across it is V. I know I. So if I sub this in here, what do I have? I have PL equals RL times V over R plus RL squared. Right? And my goal is to determine this RL such that this PL is maximized. Right? How do we maximize a function? We'll learn that in calculus. How do we maximize? We take derivative and set the derivative equal to 0. Right? So if I compute, so to maximize PL, we're going to look at the derivative of PL with respect to RL and put it equal to 0. Right? But if I look at this is a multiplication. The derivative of multiplication is the derivative of first term times the second term plus the first term times derivative of the second term. Right? So if I take derivative of this term with respect to RL is 1. So I have V over R plus RL squared. Right? Plus RL times the derivative of the second one. Right? The second one is V squared times R plus RL to the power of -2. Right? So if I have U to the power of -2, the derivative is like U prime times U to the power of -3. Right? So it is V squared divided by R plus RL to the power of 3. If I simplify it, I can factor out this V squared. I have R plus RL squared minus 2 times R plus RL times RL divided by R plus RL to the power of 4. And I have to set this equal to 0. Doing that, I know RL must be the exact same as R. Right? So to determine what the load value is, to get the maximum power, I have to choose that value to be the exact same as the value of that R. Right? This thing is called maximum power transfer theorem. So this is called maximum power transfer theorem. Right? But keep that in mind. That circuit up there could be the Thevenin equivalent circuit. Right? So if I give you a very complicated circuit with a load value that I ask you to determine this load such that it has the maximum power transfer, what am I asking you to find? I'm asking you to find R Thevenin. Because I know the only time that I get the maximum power is when this load value is the exact same as the value of R. And obviously, since I have this value, I can plug it into the power. I know power is RL times V over R plus RL. I know RL is R. So I have V squared divided by 2 times RL. The whole thing is squared. Right? RL and RL cancel, or you get V squared over 4. And this is the maximum power. This is the maximum power. And obviously, I can find current, like the maximum current. Current is V over R plus RL. I know RL is exactly the same as R, so it's V over 2R. Okay. Is that clear what's happening? Right? Let's do one quick example to see how we can use this. Example. Let's just say I am given this circuit. So 2 milliamps, 4K, 3K, and a 3 volts. And I have this RL here. The question is, find RL such that we have the maximum power. Right? What is this question asking? This is another way of asking you to find R Thevenin. Right? So I have to find R Thevenin. I already know what the load is, right? Because it tells me like it's R load, right? So I have to find equivalent across that load. So the rest of the circuit will be here. This is basically your black box, right? How do we find R Thevenin? Well, it's the case one. There is no dependent source in it. So we're going to have to zero out all the sources and find the equivalent. So the circuit looks like this. This is the 4K. This is the 3K. This is this guy. And this is open. And I have to find the equivalent here. Let's make it a little like more interesting. Let's just have like another 6K in the middle here. I want to make it a little more interesting. What is the equivalent here? What is the equivalent? What is it? Is it 10? Look what's happening. Do you agree this 6 and this 3, they're in parallel? Do you agree with that fact? So I can combine them. I have a 6K in parallel with 3K, which tells me that's a 2K. Right? And it goes between this node and this node. Right? So what is my R equivalent? Isn't it this 4K in series with this 2K? Isn't it? So it's 4K plus 2K, which is 6K. So to have the maximum power transferred, RL must be the same as R Thevenin, which is the same as R equivalent, which is a 6K. Right? Is that clear why 4K and 2K are in series? Is that clear to everybody why? Yeah? Everybody see it? So what we're going to be doing next lecture, we're going to basically have like the exact same recipe for Norton equivalent circuit. And then we're going to learn how we can go from Thevenin to Norton and Norton to Thevenin which is a theorem that's called like source transformation theorem. We're going to go through it, and we're going to do a few more examples to just make sure it actually completely makes sense. I'll see you guys Friday.